Hi guys, welcome on this channel STEM with DK Swami. So in today's lecture we are going to talk about this chapter work energy power in 11th physics. So here in this lecture we will quickly revise all the formulas related to this work energy power, and we will also discuss the concept of this work energy power. Okay, so this will be helpful for you in revising these chapter and doing the JEE mains question. And so you can watch this video, and while you are watching this video, if you wish to write down the formula, you can also write down the formula. And if you find out any confusion somewhere in any of the topic here or any of the concept, you can mention in the comments. And if you want to find out related lectures related to the this work energy part, some lectures will be available on this channel. You can search out on this channel, and you can also mention in the comments that which topic you want to understand in detail in this work energy power. So let's get started with this topic, work energy power. So in the work energy power, this chapter we first discuss about the work. So we define the work as the product of the force and the displacement in the direction of the force. So because this is a formula session where we are just revising the formula and the concepts a bit, so that's why I will quickly go through each of these things. So let's go. This work. So work is defined as force time of displacement in the direction of the force. So F vector dot ds s vector. So this is the work done because of the constant force. From here we can say one thing, that the work is a scalar quantity, and the other way to write down this same formula, I could have written down this F dot s as the F as cos theta, where theta is the angle between this. It can also be written down as force times of displacement in the direction of force, or otherwise cos theta if we put it together with force, so then we can write down force in the direction of displacement times of displacement. The unit of this is going to be joules. SI unit is joules, and otherwise the Newton meter, and the CGS unit is ergs, and we can say the relation between them. So 1 Newton meter is basically 10 to the power 7 erg. So 1 joule is 10 to the power 7 ergs. Now one more thing we know is that one other unit of this work is the calories. We know that the 1 calorie is 4.18 joules. Okay, these are the units. So now this is the work done for a constant force. What if the force is not constant? Then we will say work done because of the variable force is, first we'll find out work done for the elemental displacement. So dW will be equals to F vector dot ds vector, and then we'll say total work done is integration of the dW, so that becomes integration of the F vector dot ds vector. So by integrating we can calculate the net work done of this complete force. Okay, then what if the force is given in the form of the components like this? F vector is given to you, that F vector is Fx I cap plus Fy j cap plus Fz k cap, and the displacement is given to you as S vector equals to, okay, S vector equals to xi cap plus yj cap plus zk cap. Then we would apply this formula if the force is constant. So then we would say that the work done is F vector dot S vector. Then you will say Fx times of x plus Fy times of y plus Fz times of z. What if the force is variable? So then we will say that the work done is equals to integration of the dW. So that is integration of the F vector dot ds vector, and the elemental displacement can also be written down in the component format. So then this will become Fx dx plus Fy dy plus Fz dz. Okay, This is how I can calculate. And now here I can put the substitute the coordinates. Let's suppose we are going from x1 to x2, then we are going from y1 to y2, and then we are going from z1 to z2. That is how I can calculate the total work done. Okay. Next is, what if the force is given to you in the form of time? Okay, force function is given to you in the terms of time. Okay, so force is in the terms of time. So in that case, to calculate the work done, we'll apply the, because force is variable, so we'll say that the work done is integration of the f vector ds vector, but we cannot integrate the force function which is given in the terms of time. So for that, we will divide it with the dt and we'll multiply with the dt. So then we get the integration of the ft vt dt. Like this we can calculate. Then one more form it is, if the force displacement graph is given to you. Let's suppose this is in y direction, I have the force, and the x direction I have, this is force dependent on the displacement, and this is the displacement, or otherwise the position. So in this case, if I want to calculate the work done, so let's suppose the graph is something like this. I want to calculate the work done. Initially, the position of the particle is x1 and it is going up to the x2. I want to calculate the work done. Basically, I will say that the work done is integration of the f vector dot ds vector from x1 to x2. Basically, this integration, if you look from the mathematics point of view, it is the area under the f and the s graph. S is basically the displacement x. Okay, so this becomes the area under graph. So sometimes we'll also use, sometime in the JEE means they can also ask this question directly, where they give the force and the displacement graph and we need to calculate. Now this force is above this x-axis, so then this work done is positive. If it is below, so then the force is positive, negative, and the displacement is positive, so then it is going to be negative work done. Same goes like if the force is here, if I have somewhere here, so if the displacement, if the particle is coming from the negative direction somewhere here, and this is still the force is somewhere negative, so then the work done will be negative. Okay, so that you can understand from the direction, if the force and the displacement are in the opposite direction, so then the work done will be negative. From here we can say that cos theta, who is going to decide that the work done is going to be negative or positive, that is dependent on the cos theta. So theta is lesser than or greater than equals to 0 and lesser than equals to lesser than 90 degree. Okay, so then the work done will be a positive value. What if the angle between the force vector and the displacement vector is 90 degree? Then in that case, the work done will be, here the work done is positive, here the work done will be 0. What if the angle is greater than 90 degree? If angle is greater than 90 degree, greater than 90 degrees, and lesser than equals to 180 degree, so in that case work done will be negative. Okay, this is about complete work done. What is work, how do we calculate, all those things. Now let's go to the next thing here. Okay, so after the calculation of the work in this chapter, we go to the kinetic energy. So the kinetic energy, we define it like this. Okay, what is kinetic energy? When a particle is moving, then because of the motion, this particle has a tendency to do the work. That energy is defined as the kinetic energy, and this kinetic energy of the particle is given as half mv square, where m is the mass of this particle and v is the velocity of the particle. Now look here, this velocity of particle or the object is dependent on the frame of reference. So that's why kinetic energy becomes dependent on the frame of reference. Okay, what about the work done? We didn't talk about the work done in a relative frame. What if we take work done in a moving frame? So then the displacement would be something different. So that's why work done is also dependent on frame. Okay, it's not independent of frame. Force is independent of frame, but the displacement is dependent on the frame. So that's why the work done becomes. So kinetic energy is the tendency of the object to do the work done because of the energy stored in the object because of its motion, and this becomes dependent on the observer. It is observer is stationary, then it would be something different, and if observer is moving, so then it would be something different. All right. Now its energy, the unit is going to be same as the work. What all units we have discussed, they can also be used for the kinetic energy. One more thing is that we know the momentum. Momentum of a particle is given as mass times of velocity. So from here I can write down velocity is p divided by m. This is the velocity. Now if you place this, then we can say that the kinetic energy is basically half m, and v is p squared divided by m squared. Okay, so from here I can say p squared divided by 2m, that is the kinetic energy of this particle. Okay, so we know this. Look, I'm revising the formula, so right now I need to go like this. You might feel a bit boring, so you can try to be attentive in this, and meanwhile you can also write down these formulas. That will make you understand this formula, and then after this completion of this video, you try to recall all the formulas. That will help you to memorize, because see, in the JEE Mains, if you want to score very well, then of course you should understand the concept very well and you should be having good practice. But simultaneously, if you have not memorized the formulas, then there would be some lag. You will be lagging compared to the other students, because they know the formula, and at the same time, if you do not know the formula, then first thing is you will either try to derive it, or somewhere you will apply the wrong formula. So that's why memorization is also key thing in this JEE Mains. If you do it, so then you can do very well for the JEE Mains or the NEET, and for the advanced as well. Some formulas are required. Okay, all right. Now let's go to the next. So we have discussed about this work and the kinetic energy. Now let's go to the work energy theorem. Okay, now this work energy theorem is key factor of this chapter, very important theorem. Okay, so let's go to the definition of the work done. Work done is dw is f vector dot ds vector. This is our dw. Okay, then one more thing we know is that according to the Newton's law, if there is some object placed on this surface, and if I have applied the F force, let's go, there can also be multiple forces, then I can say net force is equals to mass times of acceleration. If mass is constant, I can say like this, according to the Newton's second law. I can say like this. All right. So according to the Newton's law, I can say like this. Then let's write down in this format. So to write down in this format, what I do is I take this equation F net equals to m times of A can be written down as V dV by ds. Okay. So from here, we can say F net times of ds is equals to m V dV. So now let's integrate both of these sides. So if we integrate both of these sides, and tell me what is this? This is our net work done. Okay, because net force, and we are doing this integration with the displacement, so this becomes the net work done. It means work done by all the forces acting on the object is equals to, now mass is constant, then we can take out, and then V dV becomes V square divided by 2 from initial velocity V1 to final velocity V2. Okay, so then I can say from here that the net work done is equals to half m, and if you put the final velocity, so V2 square minus half m V1 square. Okay, so I can say net work done is equals to, this is kinetic energy final and this is kinetic energy initial. Okay, so I can say from here that the net work done on a system is equals to change in kinetic energy. I can write it like this. Okay, so what is from here, what do we get is, I can give a statement that for a system or for an object, that work done by all the forces, then by all the forces is equal to change in kinetic energy. of system. This is our work energy theorem. So many places we apply this work energy for theorem to find out what is the velocity of the object. Sometimes the questions which can be done using the work energy theorem, they can also be done using the Newton's law and the kinematics. Okay. Now let's go to this is our work energy theorem. Now let's go to the next. Next in this chapter we define is potential energy. So before defining the potential energy, we define the conservative and non-conservative forces. Conservative versus non-conservative forces. Okay, so like we take some forces, for them the work done is independent of path. Think about it. Like for example, there is a gravity. Okay, so for the gravity, if you drop a object like this, the work done is going to be, if you place from that point to here, so the work done is going to be basically mgh. If you bring like this as well, then also the work done will be mgh. You must have got some problems like this during your classes. Okay, so and then if you take, let's suppose this page itself is the ground and you are looking from the top view, so then this is the object. And if you take this object like this on this ground, and if there is friction, then there is some work done, which will be mu mg times of displacement. And if you go like this, so then the work done will be mu mg times of this length L. Now here the work done will be something different. So here for the gravity, work done becomes independent of path. Independent of path. But for here, it is dependent on path. Okay. Then the work done here, if we take in the closed path, let's suppose if I take it like this, in case of this kind of forces, and if I take it back, so then the work done here right now is positive mgh. If we go up, so then it will be negative mgh, right? So the work done would be negative in that case. So the work done in a closed path for this kind of forces would be 0, like for example gravity. And the work done for this kind of forces will not be 0 for a closed path. Okay. So these kind of forces are called as the conservative forces. So conservative forces are those forces for them the work done is independent of path and work done in a closed path is 0. Like for example, we have gravity, then we have the electrostatic force. And then non-conservative forces, for them the work done is dependent on the path and work done in a closed path is not 0. Like for example, friction is there and then we have the air resistance. In these cases, the work done is dependent on the path. Now what happens? These forces the work done in a closed path is 0. It means what is happening? First, they are taking the work and they are storing the energy. Okay, let's suppose if we go here up, so then what is happening is work done by this force is negative. It means they are taking the energy, they are storing the energy, and while you drop this object, they give it back. So it means here these forces can store the energy. But if you come to these forces, which forces, the non-conservative forces, they will not store the energy, because basically if you release this object on the ground, so then because of the friction, it is not going to go back. Okay, so here they cannot store energy. So when they store these kind of forces, the conservative forces, if they can store the energy, then we can define a energy here that is called as potential energy. Okay. So one more thing mathematically to find out the conservative forces is that the curl of the F is going to be 0 for the conservative forces. For non-conservative forces, it will not be 0. Okay, sometimes it may be used somewhere. Okay, now let's go to the potential energy. What is the potential energy? How do we define it? So potential energy, first we cannot define absolute potential energy, we define the change in the potential energy. So change in potential energy is defined as the negative of work done by the conservative force. Okay, so this is the way we define it. You can keep it in mind like this only. Sometimes because there are the other definitions of as well in some books, where they say that this object is taken with zero velocity, and then the work done by the external forces will be equals to change in potential energy. Okay, that is also a way of defining, but right now in this chapter we will use mostly this one. The change in potential energy is equal to negative of work done by the conservative force. Okay, this is one relation. From here we can define it like this: u final minus u initial is equals to negative of conservative forces. Okay, now we define for the gravity. Let's suppose this is the ground. From the ground, gravitational force we are defining. So this we are calling it as the gravitational potential energy. Look, gravitational potential energy you will also study in the gravitation. There also we will use the same definition, but here it is for the near surface. So from the surface, at the surface we are taking height is 0, and we are taking it as at a h height from the ground, and then we are defining. So work done in this process of course is going to be mgh negative because of the gravity. So then you will say change in the potential, gravitational potential energy is minus of minus mgh, so that is mgh. So this is going to be u final minus u initial is equals to mgh, and u initial is going to be 0. Why? Because we have assumed that the gravitational potential energy on the ground is 0. We can also take this reference anywhere, so then the u becomes mgh. Potential energy at the h height from the surface or from the reference point is going to be mgh, because g is constant near the earth surface. So this is one gravitational potential energy. Then we define another is the spring potential energy. Okay, so how do we define the spring potential energy? It's like this. Let's suppose there is a spring and initially it is in the unstressed position. So right now it is in the natural length, and now you apply the force, and then you gradually expand it to a x extension. Initially it is here and finally it is here, so there is a x extension. So in this process, now if you come to the spring force is going to be minus of kx opposite to the displacement. If displacement is this direction, so then the force will be in this direction. So this is the spring force. So then the work done is going to be dw, because it is dependent on the displacement. So that's why I am applying the integration formula. So that is f vector to ds vector. So that it becomes f is minus kx and the displacement is x, dx small displacement. So net work done becomes integration of dw. Okay, so that becomes automatically there is negative because the displacement and the force is in the opposite direction. So that's why it will become minus of k times of x dx and the integration. Let's suppose the initial extension was 0 and the final extension is x. So work done by this is going to be, spring force is going to be minus of half kx square. After the solution you can get like this, and now you can say that the change in the potential energy is equals to negative work done by the conservative force. So that becomes half kx square. So then I can say u final minus u initial is equals to half kx square. Initial potential energy I will consider it as 0. So spring potential energy at the x distance is half times of kx square. So this is the potential energy. This is how we use this potential energy. Okay, for this spring. Now next let's go to the another thing, which is mechanical energy. Okay, so here we were doing this potential energy. Next is our mechanical energy and conservation of mechanical energy. So before that I am defining what is mechanical energy. So mechanical energy is defined as the sum of the kinetic energy plus the potential energy of a object or the system. So that is potential energy plus kinetic energy. Okay, mechanical energy is sum of the kinetic energy plus potential energy. Then next is conservation of mechanical energy. Okay, so conservation of mechanical energy. Let's take the work energy theorem. Work done by all the forces is equals to change in kinetic energy. right? Now all the forces, net forces, I am dividing into the two categories. Net forces can have two natures. One is conservative nature, otherwise they can also have the non-conservative nature. Okay, so I can say here likewise, because the force is of two nature, so then work done can also be of two nature because of the two forces. One is because of the conservative forces, plus work done because of the non-conservative forces, is equals to change in kinetic energy. Okay, now let's take a condition that the work done by the non-conservative forces is 0. Okay, let's take this condition that the work done by non-conservative forces is 0. So if this becomes 0, then I can say work done by conservative forces is equals to change in kinetic energy. And then from here I can say, look, change in kinetic energy plus work done by conservative force is going to negative of work done by conservative force is going to be 0. And negative of conservative force, we know that is change in potential energy. So change in potential energy is equals to 0. So we are getting change in kinetic energy plus change in potential energy is 0. Basically change in mechanical energy is 0. Or otherwise I can say mechanical energy final is equals to mechanical energy initial. Okay, this is our conservation of mechanical energy or conservation of mechanical energy. Principle of conservation of mechanical energy is conserved. But for this one, there is a condition. The condition is that only if conservative forces, this is the elementary condition for this one, that only if conservative forces are working, okay, there may be non-conservative forces, but they should not do any kind of work. Then we can say mechanical energy is conserved. Then it will be conserved. Otherwise, it will not be conserved. This is a required condition for this. Keep in mind. Okay. All right. Now let's go to the stability and types of the stability. Okay, or otherwise equilibrium. Okay. So next topic is our equilibrium. So what is equilibrium meaning? Equilibrium means the object should not change its state of motion, and right now we are talking translational equilibrium. We will also talk about the rotational equilibrium in the rigid body dynamics. Okay. So if you want to do some question on the translational equilibrium, there is a question on this channel. You can find out that related to the equilibrium. So translational equilibrium we are talking about. So translational equilibrium will happen when the state of the translation motion is not changing. Basically, acceleration of the system is 0. So for the acceleration to become 0, we can say F net equals to ma. So a must be 0. So it means net forces on the particle must be 0. Let's suppose in the net forces only the conservative forces are working. I'm just talking about the translational equilibrium under the influence of the conservative forces. So it means that the conservative force must be 0, some of the conservative forces. And now look, we have defined change in the potential energy is equals to negative of work done by conservative force. Okay, so I can say du equals to minus of dw by the conservative force, dw conservative. So that becomes minus of F vector dot ds vector. From here I can say F conservative is equals to minus of du by ds. Okay, or otherwise du by dr. Some books will also say like this, du by dr, where u is given. Now sometimes if potential energy is given in the terms of the xyz coordinates, so then we can also write on the conservative force in the vector form, that is minus of dou u by dou x I cap minus dou u by dou y j cap minus of dou u by dou z k cap. We can use this one to find out the conservative force. So what is dou? Dou is a partial differentiation. So I hope you get this. All right, yeah. So here we got this idea of equilibrium. So equilibrium means the net forces must be 0, and I am just talking about the equilibrium under the influence of the conservative force. It means the conservative forces must be 0, and conservative forces are 0. Let's suppose the forces are not given to you. Okay, just the potential energy graph is given to you, or otherwise the potential energy function is given to you. Potential energy graph or the potential energy function is given to you like this. Something we have the u r and the side is r. Okay, so conservative forces are 0, it means minus conservative forces are 0. F conservative is 0, it means minus of du by dr must be 0. So du by dr must be 0. Okay, so from here I can say, if you look at this graph, du by dr will be 0 at either the maximas like this, or otherwise the minimas, or otherwise a flat graph like this. So all these points are points of equilibrium. These are points of equilibrium. So if you have the function of the potential energy, this is by differentiating the function, you can say, you can find out the points, or otherwise if you have the graph, so then the maxima minima points would be the stability point, equilibrium point. All right, now if you look at these points, different points can have different types of equilibrium. So we primarily can have 3 types of equilibrium. Okay, so as you know, like for example, if I put something in a container like this, okay, a bowl like this, if I put a object here and if slightly displaced, then it will come back to this. So this is called as the stable equilibrium. So at the stable equilibrium, we will have the minima of the potential energy, and minima of the potential energy means d square u by dr square must be greater than 0. Okay, then we have the next one, which is the unstable equilibrium. Which is the d square u by dr square must be lesser than 0, because like if I take a bowl like this and if I put something on the top of the bowl, so then if I slightly displace, so then it will lose its equilibrium. That is our unstable equilibrium. For that it is a maximum, so it should be lesser than 0. And the third kind of equilibrium is, let's suppose you have the flat ground like this, and if you put something on the ground, then the point where you put, where it will remain in the equilibrium. So this is called as neutral equilibrium. Even if you disturb the equilibrium, so then it will attain the equilibrium at the nearby point. Okay, so for this one, the d square u by dr square must be equal to 0. Okay, so this in the graph, if you look, so this is our stable equilibrium, unstable equilibrium, and this is stable equilibrium. Then here we have unstable equilibrium, and then here we have the neutral equilibrium. All right, now this is about everything of the work and energy. Now one more thing here we define is power. What is power? Power is our rate of work done. That is rate of work done. Now whenever we define the rate of any kind, like suppose it is velocity, or it is the acceleration, rate of change of velocity, or rate of change of displacement, or rate of work done, it can be of 2 types. One is for a duration of time, that is our average, and then the other is for a particular time, which is instantaneous. Okay, so we can have the average power. Average power is basically, you will calculate the work done for a duration and you will divide it with the duration of the time. That is going to give you the average power. Instantaneous power is, P instantaneous is, you take a very small work done at an instant and then you divide it that very small time period. Basically this delta t, you take it tending to 0. Okay, so P instantaneous you get like this. Then dw can be written down as f vector dot ds vector. So from here I can say P instantaneous is going to be f vector dot ds vector divided by dt. So it also becomes like this, P instantaneous is f vector dot v vector. Okay, what will the unit of power? Unit of the power is going to be, this is our joules per second, and it is also called as the watts. One more unit is sometimes used, that is HP, horsepower. that is 746 watts. Okay, there is one more unit which is 1 kilowatt hour, but look, 1 kilowatt hour is not the unit of the power, it is the unit of energy. It is 1 kilowatt hour, it is the energy. If we take a equipment which consumes 1 kilowatt, if we run this for 1 hour, so then it will be consuming a total energy of 1 kilowatt hour. This comes out to be 3.6 times of 10 to the power 6 joules. Okay, but this is not a unit of power, don't be confused. Here I am defining the power because we have talked about the watts here. Okay, this is unit of energy. This is called as 1 unit as well. Unit of energy. Okay, what will the dimension of the work? It is F vector dot S vector, right? F unit is F dimension is ml t minus 2 multiplied by L if you do. So then the dimension of the work is ml2 t minus 2. Okay, and what will the dimension of the power? ml2 t minus 2 divided by t. So then the dimension of the power becomes ml2 t minus 3. But if you look at this dimension will be ml2 t minus 2. That's why this is the unit of the energy. This is everything in this chapter. We have talked the work. How do we calculate work for the constant force? What if we have variable force? What if we have the force in the form of coordinate? If we have force dependent on the time, force function graph is given to you, how do we find out? Then what is the kinetic energy? We have also talked about the kinetic energy. Then we have also talked about the work energy theorem, work done by all the forces is equal to change in kinetic energy. Then we have also talked about the conservative and the non-conservative forces. Then we have also defined the potential energy, what is exactly the potential energy, and then the gravitational potential energy mgh, and the spring potential energy which is given as half kx square here. And then we have also talked about the mechanical energy, which is sum of the potential energy and the kinetic energy, and then we have also talked about the conservation of the mechanical energy. This is the condition for our conservation of the mechanical energy. And then the equilibrium and the types of the equilibrium. We have the stable equilibrium, unstable equilibrium, and the neutral equilibrium. And then we have also talked about the power. This is everything in this chapter. Hope you have revised with me everything in this chapter. And now I will also upload some questions on the work energy power. PYQs, you can also post that. You can also share this video to your friends, and if you want to post the other lectures available on this channel, you can of course post that. Thank you very much.